Stepper motor torque. Stepper motor is often used in rotary actuators. Stepper motor allows to perform precise motion. The discretization of the motion depends on the number of teeth. In this stepper motor there are 88 teeth on stator and 6 poles on rotor. Stator outer diameter is 60 mm and the motor axial length is 30 mm. Energizing different coils, we can control the rotor position. Our task is to calculate the torque as a function of the rotor position. Usually the coils are energized in pairs, and in this example I will energize the coils A1 and A2 and will rotate the rotor by 0.2 degrees. I will use DC magnetic analysis and automate repetitive tasks with label mirror tool. Let's start QuickField now. In QuickField I create new problem. Problem name is stepper. Next. Problem type is Magnetostatics. Model class is plane parallel, length units are millimeters, and the axial length is 30 millimeters. Finish. On the left you can see the problem pane, and on the right you can see the geometry model editor window. You can draw the geometry model here, or you can import the geometry model from the AutoCAD DXF file. Here is the AutoCAD file already prepared, and I will import it. The geometry is imported, and you can see the cross-section of the stepper motor. Here you can recognize steel parts, coil, air block. Let's assign labels. Through labels we will provide material properties. Switch to select objects mode, click the object to select and type in the label name. This is rotor. Okay, click here, this is stator. Click here, this is air. This is the pole A1 coil. In one half of the coil the current flows in one direction, in another half of the coil the current flows in opposite direction. So I should assign different labels to the half coil blocks. On the left will be the A1 plus, and on the right will be A1 minus. I will apply the same rule to other coil halves. On the left B1 plus, on the right B1 minus, then C1 plus, C1 minus, A2 plus, A2 minus, B2 plus, B2 minus, C2 plus, C2 minus. Okay, now let's specify physical properties for these labels. Double click the label in the tree. For the air I specify relative magnetic permeability, which is 1. Okay. Stator is made of steel with non-linear magnetic permeability. I already have the data prepared here in the Excel file. Just select the data, copy and paste it here. Close. Okay, and the same steel is used in the rotor. Paste, close. Okay. Usually the coils are energized in pairs, and I will energize only the coils A1 and A2. And for other coils I will set 0 current, so B1 minus. Magnetic permeability of copper is 1 and 0 current. The same for B1 plus. The same for B2 minus, for B2 plus, and for other non-energized coils. Okay. Now for the coil A1 plus, relative magnetic permeability of copper is 1, and the total current is 4 amperes by 100 turns. Total ampere turns. For the half coil A1 minus, the same magnetic permeability and the same current, but negative. Okay. If we consider the pole A1 to be the north pole, then the pole A2 is a south pole, and the coil A2 polarity is opposite to the coil A1 polarity. Thus, in the half coil A2 plus, we have negative current, and in the half coil A2 minus, we have the positive current. Okay. That is all for block labels, but we should also assign labels to the boundaries. I believe that magnetic field is contained within steel parts and there is no magnetic field outside, so I will assign label to these edges 0. To select multiple objects at the same time, hold the control button pressed. Okay, for this label I specify 0 magnetic potential. Okay. Geometry model and the data are ready, and before I start the analysis I should build the finite element mesh. Just click this button. Now save all problem files and run the analysis. The problem has been solved and we can take a look at the results now. Here you can see the magnetic field lines, and you can adjust the field picture, switch on, for example, the color map of the flux density and the vectors of the flux density. The correspondence between colors and numbers you can see in the legend. And you can get exact values of the field parameters. If you use the local values tool, just click any point, and here is the point coordinates, flux density, field strength and other parameters, and you can edit the point coordinates here. You can also use the contour tool to extract field parameters. Switch on the contour tool, change line type to be the straight line, just draw the contour line here across the pole, switch on the XY plot, and here I can get the flux density distribution in the pole. Exact numbers you can see in the table. Coordinates, flux density components and other field parameters. You can also construct contours specifying the coordinates manually. Contour clear, contour add lines. First point will be minus 23.7 here in the A gap, and another point will be on the right, and I specify the line type to be the half arc. Add line. Here you can see the contour was constructed in the A gap. Now I can get the flux density distribution in the A gap. Here it is. Okay. You can also use contours to calculate integral values. Contour clear. I will click here to select the rotor. Click to select the energized coils. Now follow to the integrals, and here is the mechanical torque acting on the rotor. The rotor teeth are aligned with the stator teeth, so the torque is very small. But now I am going to rotate the rotor and the torque will change. To rotate the rotor I open the geometry model, switch to select objects mode, click the rotor and the coils. Remember to hold the control button pressed to to select multiple objects at the same time. Now follow to the edit, move selection, rotation by 0 to 0.2 degree. OK. The rotor was rotated. Now let's build the fine element mesh in the air. Save all problem files. Run the analysis. The problem has been solved. Open the results. Use the integral tool. Click to select the rotor. Click to select the energized coils. Follow to the integrals. Mechanical torque. Now you see the value has changed. There is a way to automate the calculations. QuickField has the label mover tool for parametric analysis. The workflow is simple. First, choose the base problem. It's automatically set to our active problem now, stepper.pbm. Now choose the values to measure. Add values. I would like to measure the torque acting on rotor and energized coils. A1 minus, A1 plus, A2 minus, A2 plus. OK. Mechanical torque. Add the value to measure. Close. Record steps. In fact, there is no difference what you will rotate, rotor or the stator. I will rotate the stator. Rotation by 0.2 degrees. Add step. Close. And I would like to repeat this step, say 20 times. OK. Now I need only to press Get Results button, and label mover does the rest. The set of problems is generated. In each problem the stator is rotated. The problems will be then simulated and the torque will be measured. You see, several problems are simulated at the same time. That's because on my computer the 4-core processor is installed. And you already see some results are stored in the table. Everything is done, and here is the dependency of the mechanical torque on the stator position. You can see the dependency on the plot, and here you can find the maximum value of the torque, which is 0.12 newtons meter. The intermediate results are stored in the separate folder, and for each result you can open the geometry model and you can view the field distribution. This is the rotor position where you get the maximum torque. The same value you have seen in label mover. And you can copy all these data and don't forget to save the label mover file. If you search for the stepper motor torque on our website, you will find the example page. Here you can read about problem setup, browse the solution section and take a look at the resulting pictures. And you can download the simulation files here. Simulation files may be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition that you can download from our website for free.